Happy to have Mike Hudson today, professor at the University of Waterloo. Mike works on weak lensing, and dark-side halos, and Untitled Chapter. And today is going to tell us about what peculiar velocities tell us about cosmology and gravity.
Great, thanks. It's always a pleasure to come back here. Cosmic flows is an area where I started my career, and then I kind of mostly put it aside for a while. I've now coming back into it a little bit, and I'll try to convince you that that's not a crazy thing to do. Was anybody here? I noticed that Hume Feldman was a speaker a few weeks ago. Was anybody here at his talk? A few of you are nodding, about half of you. Okay, so part of my talk has some overlap. The other 2/3 is different, but I'll go sort of quickly through the stuff that overlaps what he might have talked about, because we collaborated on a few papers. So I'll give you the intro and motivation. I'll tell you about bulk flows and why we care about them, and that's the stuff that Hume talked about a few weeks ago. Then I'll talk to you about how peculiar velocities measure infall into superclusters, and how you can learn cosmological parameters by comparing that measured infall to predictions from maps of galaxies. And then the last part of the talk, depending on how time goes, I'll talk about the kinetic Sunyaev-Zeldovich effect, which is a different and new way of measuring peculiar velocities. So most people know this, of course, already, but just to get you on the right page, you all know that the local group has a motion of 600 kilometers per second. With respect to the CMB, we measure a few, was it 400, I think, is the sun's velocity with respect to the CMB, and then there's some transformations. When you get into the frame of the barycenter of the local group, after taking out the galactic rotation and the infall of our galaxy towards M31, you get this number of 600 kilometers per second. And of course, in the standard picture, that's thought to be generated by fluctuations, perturbations, which lead to peculiar velocities, including the peculiar velocity of our own local group. Some people used to ask about, well, could it be an intrinsic effect in the primordial CMB itself, perhaps some weird, very large-scale perturbation? I think that is now, so that possibility is now ruled out because one sees in the power spectrum itself the effect of our motion through the aberration of the angles and the Doppler boosting of the signal. So it does indicate that that's the actual motion of the sun itself, rather than some primordial large-scale gradient. Okay, so we think this should be then due to the peculiar velocity of our local group. So another way to phrase this question then in that context is, from a purely observational point of view, what is the source of this motion? What are the structures that are responsible for it? That's the, if you like, the cosmographic question, as opposed to the statistical perturbation, where we care about the amplitude of the fluctuations and their phases. Where are the actual structures that are responsible for this? And it's, of course, related to this more fundamental question of what scale do you have to go to where the universe is on average at rest? That you've included all of the important sources of the motions, the peculiar velocities of nearby objects. Of course, you never quite converge, but you would like to get close to the asymptotic value. In lambda CDM, you predict contributions from a whole range of scales. So you're never going to get exactly the this is about 627. You're never going to get exactly the 627. But you'd like to see yourself get close, because that means you've surveyed a volume which includes all the major fluctuations in the nearby universe. Okay, and so peculiar velocities then are important because they're really the only realistic way to probe the large-scale distribution, not of galaxies, but of mass in the nearby universe. Because it's those mass fluctuations which will generate it. The other one that's comparable, of course, is a integrated Sachs-Wolf effect, but that's a very tough measurement to make. This has higher statistical significance. So in principle, it's a good way of probing large-scale fluctuations, not in galaxies, but in mass itself. Okay, so just from a cartoon perspective, if we start from this idea that the local group is moving at 600 kilometers per second, the problem with that measurement is that the peculiar velocity of a single object, the local group, doesn't distinguish between the possibility that you have nearby sources of gravity of lower mass or more distant sources, presumably of higher mass. Okay, so it could be something relatively close or something farther away. So to go beyond this, we want to actually map the velocity field itself, the peculiar velocities of other objects other than the local group. And from a cosmographic perspective, that will help us distinguish between infall, whether the local group's motion is due primarily to infall into a local attractor, or if, for example, you measured a coherent motion, a sort of a mean motion over a larger volume, then that would suggest that there are distant sources which are primarily responsible for the local group's motion. Of course, in a lambda CDM model with Gaussian fluctuations, you expect all scales to be important, as I said, but depending on the power spectrum, the larger or smaller scales might be more or less important. Okay, so just to remind you how, most of you I'm sure know this already, here's the formula in linear perturbation theory, that the peculiar velocity is proportional to the peculiar acceleration. Okay, so it just depends on an integral over the fluctuation rho minus rho bar of the mass within 1 over r squared, just like in normal gravity. So that's cool because it means that if you measure this guy here, you can learn about two different things. The actual fluctuations in the mass itself, and this prefactor here, f, which is the logarithmic rate of the growth of the perturbations. Okay, so that's the growing mode, and this is the logarithmic rate. And in lambda CDM, this quantity turns out to be proportional to the omega matter if it's flat lambda CDM to some power gamma, where gamma is 0.55 in flat lambda CDM. Okay, so in addition to measuring the cosmological parameters, if you can measure this guy, you might be able to distinguish other alternative models of gravity, which might make different predictions for how the perturbations grow as a function of cosmic time. You know, in particular, if something funny is happening at late times, maybe you have a different, you have your own theory of gravity which predicts, say, the acceleration in, supposing it's nothing to do with lambda, some alternative gravity model, then that alternative gravity model may predict a different growth rate of fluctuations which you might hope to measure. And that might only appear, it might only manifest itself perhaps at late times if you wanted to explain dark energy. So you might not see that in the CMB, for example, but you might see it in the present day universe. Okay, that's to motivate the theorists. All right, so peculiar velocities. I'm going to talk this, most of the talk is going to be divided into two chunks. Okay, so the first part about bulk flows, the motivation for that is really looking primarily at the matter power spectrum on very large gigaparsec type scales in the low redshift universe. Okay, and the second part of the talk will be measuring about the growth factor and the fluctuations on 8 megaparsec scales in the mass, sigma 8. Okay, let me talk about the bulk flow first. All right, so just to get you all on the same page, what is a bulk flow? Bulk flow is the average peculiar velocity of some volume. Okay. Individual peculiar velocity measurements we'll see are quite noisy. For a single object, they're good to only 10 or 20% of the distance. Okay, and so in the when I'm talking about the nearby universe, I'm talking about 100 h inverse megaparsecs. That's a recession velocity of 10,000 kilometers per second. 10% of that is 1,000 kilometers per second. So that's a big number compared to the actual motion of 600 for the local group. So on very large scales, individual measurements don't tell us very much. We have to average, right? And so the bulk flow being an average will beat down the noise. And the nice thing about the bulk flow, the mean peculiar velocity, you can think about it as the mean proportional to the mean peculiar gravity, is it's sensitive to fluctuations which are on scales larger than the structures that you're probing, right? Because if you think about a volume, and you think about some sources inside it, they'll have gravity in and out of those sources, so the average will cancel to 0, and only the large-scale waves will remain. So if I measure, crudely speaking, if I measure the bulk flow on 100 megaparsec scales, I'm probing the matter power spectrum on scales larger than that. Now the problem with this in practice, implementing this in practice, I'll come on to in a second. Okay, so let's write it still wearing our theorist hat. You can ask yourself, what do you expect in lambda CDM for the bulk flow of a sphere of a given size? Okay, so that's given by this expression here, which, like many of these scenarios, you've got an integral over a power spectrum, some window function, okay, which depends on the survey geometry. Now the difference between this and the equivalent expression for density fluctuations, like in an 8 megaparsec sphere, is that this has 2 less powers of k in it. Okay, because the velocity goes like the density fluctuations divided by k. So you're automatically, just from the form of this, more sensitive to lower k, i.e. larger physical scales, right off the bat. Okay, that's the power of looking at the large scale stuff. And so this guy will depend on the geometry of your survey, and I'll come back to that in a few minutes, and Hume would have talked about that in great detail. So just to give you some reference, if you could design this, a window which was the shape of a Gaussian, let's say Gaussian with a radius of 50 h inverse megaparsecs in lambda CDM, and it doesn't matter much whether it's a WMAP normalized or a Planck normalized, because they only differ by some number less than 10%. The typical RMS that you would get is 100 or 110 kilometers per second in each of the 3 x, y, z Cartesian components. Okay? So we expect a mean of 0 with this fluctuation for different spheres placed around the universe. Now the problem is, for at least conventional methods of measuring peculiar velocities, is it's a little bit like the CMB quadrupole. We only have one measurement of the, the 5 components of the quadrupole. Here we only have one measurement, i.e. the sphere centered around us, of the measurement of the bulk flow. Okay, so we're going to make a measurement, and the comparison point is, what is the RMS that you would expect had you lived at different places in a lambda CDM universe? And is the value you measure unlikely or not? Okay, so normally, if this is the value in each of the 3 vector components, you might expect that the typical amplitude would be about square root of 3 times that number. Okay, so you'd expect typically for a 50 h inverse megaparsec Gaussian, something like 170, 200 kilometers per second would be a typical value. If you measured 300 kilometers per second, you'd still be okay, because this has some fluctuations around it. There's only 3 degrees of freedom. On the other hand, if you measure 400 kilometers per second, that turns out to be quite unlikely. Okay, and you can calculate that crudely by thinking of a chi-squared with 3 degrees of freedom, with a mean of 0 and a variance of around 100. That's a little bit more, typically 110. So this would be something under a chi-squared of 16 for 3 degrees of freedom, which is improbable. Okay, that's just reference, because we're going to come back to these numbers later. All right, so now we actually have to measure this thing. Okay, so this is very theoretical. In practice, what do you have? You don't really have the average peculiar velocity of some volume. You have a bunch of measurements of peculiar velocities, right? So just to remind you of the definitions. So from the perspective of measuring these things, CZ is easy. Take a redshift, that's no problem. The hard part is H naught R. Okay, particularly the R. In fact, the Hubble constant turns out to drop out of all these calculations if you calibrate this guy in kilometers per second. So this thing here, you measure either with supernovae, which are typically good to 10%, or the Tully-Fisher relation, or the fundamental plane. So you might think, oh, supernovae is the way to go. The problem with supernovae is that you can't make them go off when you want to, right? If you do Tully-Fisher for spirals or fundamental plane for early type galaxies, you just go and make your measurements and you're done. Supernovae are serendipitous. You have to wait for one to go off, and they don't go off very often. Okay, so you get 1 per L-star galaxy per 100 years. That means to survey all the L-star galaxies, you have to wait 100 years. And we haven't been looking at them that long. On the other hand, in the far future, if you're willing to wait 1,000 years, every galaxy will have had 10 of them by then, and so you can continue to beat down the errors, whereas with these guys you can't. Problem is 1,000 years is longer than your average graduate student's time scale. So this is the method I'm going to talk about in most of this talk, direct distance system estimates. There's a second method which I'm going to use the results of, but I'm not going to talk about very much. And that's a statistical method that many of you will be familiar with, redshift space distortions. Right? Does everybody know what redshift space distortions is? Yes, collapse along the line of sight of structures. No redshift space perturbations perpendicular to the line of sight. It's fully explored by Nick Kaiser, who's a former citizen from way back in the early days. Okay, so if you measure statistically the enhancement of structures that are along the line of sight versus the ones perpendicular, you get a measure of the average amount of collapse, which is a measure of the typical peculiar velocities. It's a powerful and simple method, but because it's a statistical measurement and you're essentially measuring a power spectrum in two different directions and comparing them, you need a very large volume to average over cosmic variance. Okay, but nevertheless, that's one way. And the last one, which I'll talk about right at the end, which is still in its infancy, is the kinetic Sunyaev-Zeldovich effect. Okay, so let's come back to the direct distance estimates. And I'm going to show you some data so you get a feeling of what it looks like and the effects of sparse sampling. Okay, so this map here is a model of the peculiar velocity field. It's not actual measurements. It's based on measurements of the galaxy density field coming from a redshift survey. And that galaxy density field is used to predict the peculiar velocities, which are all the arrows. Okay. Now, you would like to take some volume of a given size and average the actual measurements there. The problem is that the real measurements, which look like this, are sparse and noisy. Okay, so here's a survey. This is a survey I led many years ago. It's based on clusters of galaxies. So just to orient you, things that are red have a peculiar velocity outwards. Things that are blue have a peculiar velocity inwards. The distance, h0 times r, of a given object is where the dot is. And the tip of the arrow is at CZ, so the difference between the two is a peculiar velocity. These are based on fundamental plane, and they're an average over many objects in a cluster. But just to orient you, had they represented just a single fundamental plane object, the errors typically, I said, are 20%. Okay, so they typically would be that large here. So if this was a single object, it would be a signal to noise of 1 type of measurement. And the ones that are like this would be much smaller. So you can see that it's noisy, and the sampling is sparse. Okay, here's a different survey, just to give you some reference. Different survey called EFAR. These, again, are a little bit old. This only observed one hemisphere. So the traditional problem in this field, historically, was that people didn't and couldn't measure the mean bulk flow of the entire volume because they didn't have measurements of the whole volume. What people would do was measure the mean of some set of objects. Okay? And here are the set of objects. And so that gives you an average motion or bulk flow of a sample, not of a volume. Now, if you know what your sample geometry is, you can still calculate the window function that I showed you before. Okay, and Nick Kaiser worked that out way back when, in the 80s. And he did it for the simple case, which is what most people do, which is you weight the objects by 1 over the square of their errors. Okay? Problem with that is it gives a lot of weight to the things that are nearby. Because the errors go proportional to distance, and so that weight goes as the inverse square of distance. Very large near to the origin. Okay, so and this is what Hume would have talked about a couple of weeks ago. What we did is come up with a new method of accounting for this sparse sampling, specifically constructing an optimal weighting scheme. You don't have to weight them by 1 over the square of their random errors. If your goal, for example, is to say, given a set of objects within some volume, and I want to know how best I can the bulk motion of that volume, I can choose how I weight each point to minimize the variance between that weighted mean and the actual volume that you would like to probe. Okay, and that's a well-posed problem, and you can solve for those weights. All right? So that's what we did with Rick Watkins and Hume. We constructed the scheme to change the weights And that not only allows us to get a better estimate of the mean motion of the volume, but it allows us to compare different samples. Okay? So when we did that, we compared a bunch of different surveys, and we found that most of them agreed, once we allowed for this sampling geometry, agreed with each other, and we put them all together into a master sample, okay, which we call composite, and we measured with this minimum variance scheme the bulk flow of a 50 megaparsec Gaussian. Okay, and that number was 400 kilometers per second, plus or minus 80. Okay, now this turns out, if you compare to what your expectations, allowing for the weighting scheme and the residual, you know, your most optimal weighting scheme is still sparsely sampled. It's just as close as you can to this idealized survey geometry. It's not perfect, so you have to allow for that. When you do all those calculations, this flow is 2% likely in lambda CDM. Okay, so taken at face value, assuming the data is fine, there's two interpretations. Lambda CDM is not correct, or we just happen to live in a special place in a lambda CDM universe, and it's unlikely at about the 2% level. Okay. Now, at the same time, as we were doing this, and independently, a different approach was taken by Kashlinsky. He tried to measure the kinetic Sunyaev-Zeldovich effect, which I'll talk about later, from clusters of galaxies. Okay, and he found this whopping velocity of his sample of clusters that extended to a much larger scale. Okay, 300 to 500 megaparsecs. Wasn't exactly clear. He thought, that's kind of strange. And one of the strange things was that these two, I haven't listed them here, but the directions of these two flows happen to be in very close agreement with each other. They agreed to within 6 degrees. Which, if they were both garbage, both random vectors, is very unlikely. Okay, so I thought, well, maybe the amplitude is very uncertain, because what he's actually measuring is a temperature decrement, and you have to make some assumptions about how many electrons are along the line of sight, and that's quite uncertain, especially with beam smearing and so on. So one possibility was his direction was fine, but maybe his amplitude was off from some unknown systematic error. Maybe he was really measuring 300 or something like that, although admittedly on a very much larger scale, which would have been even more unlikely in lambda CDM. So the answer to all this stuff, of course, is to not debate too much about the statistics, but to go out and get more data. And so when a new survey of supernovae came out, I put my student on this. And he applied the same method to a bunch of supernovae that were mostly independent of this, but not 100%, and came out with a much lower number. Okay, which was not, this number by itself is consistent with this number, but on the other hand, this number by itself is also consistent with lambda CDM. Okay, so it doesn't fully answer the question. It could be that the truth lies somewhere in between these two, in which case it's still slightly unlikely, but less than 2%. Maybe if you take out the supernovae in here to try to make the samples, the whole sample not have duplicated data, it becomes, instead of 2%, maybe 5 or 6% likely. So the discrepancy goes down, but doesn't completely disappear. Subsequent to that, more data have come out. Okay, so this is Watkins and Feldman. This is, I think Hume talked about this a few weeks ago. Same method again, same scale, but using a different data set of distances called Cosmic Flows 2. That's done by Brent Tully. This also gives you a lower value. Okay, and it's not completely independent of this. The actual objects are not complete. A few weeks ago, I think it was, I saw this one on the archive. So this is a different survey. 2MTF is a Tully-Fisher, that's what the TF is, survey drawn from 2 mass galaxies. Again, the data are not completely independent because many of the same spiral galaxies used for the Tully-Fisher are in this sample with recalibrated distances, and many of them were in this original sample. Okay. Oh yeah, that's a good question. So in this case here, there was about 5,000. and by an object, I mean a group. If it's a cluster or a group, I mean I've averaged the fundamental plane or the Tully-Fisher for the whole group and call it one object. So they're not all of, each object is not of equal quality. This one, I can't remember how many clusters, maybe 700 clusters, I think. This was 250 supernovae, because the supernovae have much smaller errors. This is again around 5,000. This is a little bit less than that. I forget the exact number. And this number here, which is unpublished, is from the 6DF survey. Scrimgeour was a postdoc. She's moved on now, but she was working with myself and Nayesh Afshordi in Waterloo until recently. And so her fundamental plane measurement, which is more or less independent of all of these, is done based on 9,000 objects, but they're a little bit more distant. So the error in kilometers per second per object is on average larger, but the sample's big. Okay, so she also seems to measure a lower value. This one's intermediate, and these ones are low. So my conclusion at the moment from this set of data at present, is that there's no need to panic. Okay, if you're a lambda CDM advocate, given the whole suite of data, there's no conflict. The other thing that's worth mentioning, as it says here, is that while the amplitudes differ, and the data sets aren't admittedly completely independent, the directions found for most of them are consistent with each other. It's just the actual velocity, the speed, if you like, which is distinct. So there's no substantial evidence at present. The numbers are still a little bit high, but not out of the normal variance range that you would expect from lambda CDM. As I said, you would expect 170 or 200, and these numbers are 250, 300, maybe a little bit higher.
These are just statistical.
These are, there's no cosmic variance in this. This is sort of the uncertainty in the measurement versus what you would expect for an idealized sphere of radius 50 H inverse megaparsecs. So everybody's now using the same method that we implemented first in this paper here. Okay, so it was more fun when it disagreed with lambda CDM, but this is what the data say. So that's, at the moment, that's where the bulk flow story stands. So now I want to switch gears and talk to you about a different type of measurement you can make with the same data set. And that is by comparing velocities with the predictions from a galaxy density field. So if you like, you can think about it as a carrelation between a density field and a velocity field. Okay, and this is work led by my master's student, John Carrick, PhD student, and Guillaume Lavaux, whom many of you may have met when he was here a bit more than a year ago. He was a CITA National Fellow. He's now a faculty in Paris. Okay, so let's go back to this equation. So for this part of the talk, I'm going to assume that the fluctuations in galaxies are related linearly with linear biasing to the fluctuations in the mass. Okay. Now, if I have a map then of these galaxy densities, I can use that map with this assumption to predict what the velocities are. Okay. I've got this annoying extra b factor here. And this is degenerate with the f, so I'm going to call that beta. Okay? And in practice, my galaxy distribution doesn't go out to infinity. It goes out to some finite distance. So there's contribution from Rmax to infinity. But if the edge of the survey is far compared to where the peculiar velocity data are, I can expand that. And the lowest order term that's important is just a dipole, because the quadrupole will fall off as r cubed. So for simplicity, I'm just going to model the rest of the stuff as like a bulk flow vector, but it's like now a residual bulk flow. It's the part of the motion that isn't explained within Rmax. Okay, and for the data I'm going to talk about, Rmax is 20,000 kilometers per second, or 200 H inverse megaparsecs. Okay, so we went to a lot of effort to make a new survey by compiling. So that, let me before I get there, the point is, as I said, oops, my thing's gotten moved. That and that are measurable. Well, that and that are measurable, and they give you these two quantities here, which are derived from the data. And this guy here you can convert into something more useful. Okay, so if we assume linear biasing, then the sigma 8s are related. And since beta is f over b, I could rewrite the b in terms of the sigma 8s. Okay? And at the end of the day, sigma 8 of the galaxies is itself measurable. If I have my map, I can go and calculate what that is. Okay, the beta is going to be measurable. So that's measurable just from the density map of galaxies alone. And this guy is measurable by comparing those predictions to observations of this. All right, so if I put those two things together, I get this quantity F times sigma 8. It's a degenerate combination, but still important, as we'll see in a second. Okay, so those two guys are both measurable. All right, so in practice, F and sigma 8 for a given cosmological model both depend on Z. So if I measure them from my data set, that's effectively Z of 0. It's really Z of 0.02, but let's call it 0. Okay? On the other hand, if I can combine it with other measurements of these quantities at different redshifts, we can break this degeneracy. All right? So in this little bit, I'm going to show you what happens when you make this. So we've done this measurement from an earlier data set. We've measured beta, and then I'll update you with the latest values from the current data set. We've measured beta. We've gone through this exercise and calculated this at redshift 0. And then we're going to add it to peculiar velocity data at other redshifts. Okay? So this is what you get. This is from an older paper from a couple of years ago. If you plot at what was available at the time, all the measurements of F sigma 8 onto a single diagram. Okay, so here was our measurement. All right, this is another measurement from peculiar velocities at low redshift from Davis, Nusser, Masters, et al. The rest of these are all measurements from redshift space distortions. Right? We can't use the conventional peculiar velocities at high redshift because of the fact that the distance errors scale linearly with the distance. So they quickly blow up at large redshift. Some of these are not so old. This has now been updated a little bit. That's, for example, the BOSS measurement. Okay, one thing that's worth remembering about all this is that all of these redshift space distortions is close to 1 million redshifts to make this measurement. Right? Whereas this stuff here was only of order of 5,000 peculiar velocities. And the error bars are not very different here from these other surveys. Okay, so one of the takeaway points is that because this is a cross-correlation method, it's not a comparison of two autocorrelations in two different directions. It's not subject to any cosmic variance. So it's actually quite powerful on an object-by-object basis. These are great methods, but they're statistical, and so you need to sample large volumes with huge surveys. So if your goal is to measure this guy, and I'll try to show you later that you get a lot of if you fix this thing in the CMB, you get the most leverage also if you do it at low redshift. There's some value to this approach. So this shows you how you can use it. So let me go back here. So this curve here is lambda CDM normalized to WMAP. So that's taking the WMAP values of F, okay, and the WMAP values of sigma 8 and projecting forwards. But if you forget about CMB, you can actually fit this curve itself from this data alone, not using the CMB at all. All right? And if you do that, you get the following diagram. You get contours in the sigma 8. This should say been cut off. It's omega matter plot. Okay, so if you didn't have the low redshift stuff that I showed you, these 2 points here from direct peculiar velocity measurements, you'd get this larger curve here. Once you include those, you can strain the parameters more by including those very low redshift points from direct peculiar velocity measurements. So all this is only coming from peculiar velocities. There's no CMB in it at all. Okay, no assumptions about what sigma 8 should be. So that's quite nice. At the time we did this, Planck wasn't out. So WMAP, here was the measurement. WMAP is here, and I've put on more or less by eye, by hand, where Planck sits just outside of this 95% confidence region. It's good because the other reason this is interesting is because most of the classical cosmological parameters come from geometric methods. Right, like supernovae distances or BAO using it as a distance scale. This is a measurement not from a geometric method, but purely from the growth of structure. So in other words, in using this data, I'm not, for example, in BOSS, I'm not using any of the BAO information, I'm using the compression along the line of sight, the redshift space distortion part of the signal, which is not geometric in the same sense. Although you have to assume a geometry to fit it. So it's an independent measurement. It's coming only from the growth of structure, and that itself is a test of gravity, because if you had a different gravity model, you might get different growth of structure, and so you'd get a different curve in here. I don't have it plotted here. I think I omitted that diagram, but if you plot this for the old DGP, Diwali, I can't remember what the G and the P are. So it's an alternate gravity model in brain world. Most of you guys may have heard about this. It's old. It's ruled out through other methods, but it's also ruled out through this. It goes down here. It does that for two reasons. One, the gamma is wrong. So F is sigma 8. F is omega matter to the 0.55, and in DGP it's to the 0.69, but also its Friedmann equation's different. Okay, so it's strongly ruled out down here somewhere. And you can use, this is what it says here, so you can also use this to measure this gamma directly. Even if you have some other model which predicts a different growth, you can actually, if you use the CMB to fix sigma 8, then you can fit for this as a different parameter. Well, this you do need the CMB. And if you do that exercise, this is what we found at the time, mapping those measurements into now measurements of gamma. Okay, from the different surveys, right? And you see you get fairly small error bars from the stuff that's at low redshift. Okay, so from this data set we measured 0.62, which unfortunately is which is consistent with the lambda CDM value, but also is consistent with the higher value here. So that itself is not ruled out, but DGP, the model, is because of the different Friedmann equation. Okay, here's a recent analysis using a different subset of data, including updated values from BOSS. Comes with a very similar number, but it didn't use our data at very low redshift. Okay, so this has potential as you improve these measurements to make tighter and tighter constraints on the growth of fluctuations, and hence test alternative models for what gravity could be doing on large scales. Where you might think that if it was doing anything different from lambda CDM, maybe on large scales is where it's doing it. Right? If you want to account for acceleration, for example. Okay, so this was old as of 12. Now I'm just going to update you on this point here. Okay, from our survey. So this is now the deepest all-sky redshift survey, and it's not quite all-sky. It's a combination of 3 different redshift surveys. The 2-mass redshift survey, as the name implies, is from the 2-mass catalog. Goes to a K-band of 11.5. That's all the stuff in red. Okay, and to that we've added the 60F galaxy redshift survey, which goes a magnitude deeper, and we've cut Sloan to about the same magnitude. So roughly 2/3 of the sky is covered by the deeper stuff, and 1/3 of it's still shallow. And the problem is there's no good spectrograph, multi-object spectrograph, to finish off this stuff. 60F is in the south, but there's nothing in the north. I suppose Sloan could do it if it wanted to, but it's doing other things. And so for the first time, we're getting out to very large distances, 200 H inverse megaparsecs. So if you take a slice through the supergalactic plane, okay, so we live here at 0, 0, and supergalactic coordinates are chosen to have interesting structures in them. They're ironically originally defined by de Vaucouleurs based only on this little piece of the universe, but even now out to 200 H inverse megaparsecs is still true that the most interesting structures are still in the same plane that he defined, which is kind of cool. So this is the map that you get if you take the density field of galaxies, you smooth it with a Gaussian of 4 H inverse megaparsecs, and I'll try to justify that in a second. Okay, and then you take a slice through it in the supergalactic plane. So we live here. That's Virgo. This is the Hydra Centaurus, or Great Attractor region, for those of you who are local structure aficionados may remember. This guy down here is Perseus Pisces. In the old days, this is going back a little bit, in the old days of people would talk about the tug of war between these two structures. The important thing with this survey is it now reaches out to include this guy here, which is called the Shapley concentration. It's the biggest supercluster in the nearby universe. And it's been known to be an important concentration for a while. It's named after Shapley, who discovered it. But it's only now that we can accurately sort of assess its overdensity in galaxies and see how much it contributes to the motion of nearby objects. They're not significance level. I forget what the contours are, but we could probably guess them by looking at the chart. But they're not significant spaced. So some of this, especially at large distances, is noise. And this part here is the part that's covered by this shallower 2MRS part, and that's why it cuts off at this distance. Okay, so just to have a little bit of fun and to guide you through, this is what happens if you take now slices going through stepping through in supergalactic Z. It's kind of neat. When we get down to 0, you'll see Shapley coming up right about here. There it is. Bing. That's the biggest thing. Okay, but structure looks Gaussian on the whole. Looks like a Gaussian random field, or how you might imagine. That's horologium reticulum. That's another important one. Some of you may have heard about ideas that the local volume may be underdense, and that the underdensity may drive an apparent acceleration, which isn't real. Within this volume, we don't see any underdensity. So this is the density in independent shells. Okay, with no error bars plotted, but you can guess from the scatter what the errors are. All right, and so they seem to scatter around a density contrast of 0. So we don't find a big void, at least within this volume. It doesn't rule out that the volume is totally embedded in a void, and it's, that's a slightly larger scale, but that seems a bit contrived. So how good is this? If we go back to here, we have this as our model for what the velocities are going to be. I put in a delta, and I told you it was smoothed. Okay, so what smoothing should you adopt? We did some tests on n-body simulations. And if you compare halos, which are these curves down here, you compare the observed velocity of those halos to the predictions as a function of the smoothing length that you smooth the density field, because you're applying linear theory. Linear theory is not valid on small scales. On the other hand, if you smooth too much, then you're suppressing real power, right? Real signal. So the answer comes out to be a 4 megaparsec Gaussian, and the predictions should be good to under 100 kilometers per second on an object-by-object basis. Okay, so now you can ask the question, given the map that we've seen before, if I take just the local group, okay, and I just look at the dipole at the local group, at the origin, and I go to ever-increasing spheres, okay, I can predict what velocity the local group should have from the matter out to that radius, all right, which is here. And we expect that as that goes to infinity, we would recover the local group's motion, which is 600 kilometers per second, maybe plus or minus that 100 and just under 150 that I showed you before, because it's a linear theory prediction for the local group. Okay, and so that's what that curve looks like as you include more and more matter. You can see that by 200, we're getting fairly close to where we should be. We're a little bit short, maybe 100 kilometers per second short, according to the local group. And the curves here are what you expect in lambda CDM. Okay, so in lambda CDM, you also expect to be fairly close to there by 200. And you sort of asymptotically reach 600 at larger distances. Of course, this depends on the prefactor you put in front of it, that value of beta. And we'll see later on that this cyan value, which corresponds to 0.45, is the one that's fitted by fitting other data sets. So those other data sets are spiral galaxies that I talked about before, SFI++ sample it's called, and the supernovae that I mentioned previously. There's about 4,000 of these and 250 of those. So we can do it point by point. We can make the comparison point by point. On the whole, when you do that over the entire sample, the chi-squared turns out to be quite good. The reduced chi-squared is actually better than 1. So this is one particularly interesting region. It's interesting because it includes the Shapley supercluster. This is a cone of data. It's not the whole data set we have. It's a little cone along an interesting direction, which corresponds roughly to this axis here. Okay, so if you make the comparison of observations and predictions, which are the colored curves, this is what you get. There's good agreement in most places. There are some regions where it may be slightly discrepant. It's hard to know if that's just a statistical fluke or whether it indicates a systematic. The blue curve is what you get if there's no external motion, and the red curve is a better fit if you allow some residual motion to come from outside the volume. So you have another 30 of these. This is just to show you one of the more interesting ones. Overall, the chi-square is quite good. So this amplitude of these curves, they get shifted by this V external, and the amplitude gets scaled by that factor beta, so you can fit for it. And when you do it and you go through the same process that I described earlier, you can convert that into an F sigma 8. Okay, and so now we're measuring for this quantity 0.4 with smaller error bars than what we found previously. And by chance, it's exactly the same value. Okay, so we already saw that this point was consistent with lambda CDM, and so this point is as well. And that tells us that this infall measurement is giving us cosmological values which are again consistent with the lambda CDM model. But now the scale that we're probing is not these very large scales, but rather the scale of infall into these structures, right? Maybe 20 or 40 megaparsecs. Here's a summary slide that shows a bunch of different measurements of these parameters, now assuming an omega matter of 0.3, okay, from different probes that roughly probe, this is roughly organized from small scales up to large scales by twiddle my guesswork, right? So lensing, CFHT legacy survey, another project that I've been involved in, measures this value, and that's probably the smallest scales. Here's a bunch of measurements from clusters. Okay, here's the measurements from peculiar velocities. Okay, these are the older ones I showed you. And this is the one I just quoted. And this is what you get if you take all the redshift space distortion measurements and put them all together. Okay, so this is the 1 million redshifts, and this is the roughly 5,000 peculiar velocities. Similar error bars. Okay, and then CMB, WMAP, and Planck. So maybe if you wanted to, you could think maybe there's a curve through there. I don't know. Neutrinos. Well, these two should be on the same scale, but they've had to be plotted off just for plotting convenience. And I think this is bigger than this. The Planck one could be wrong. Right?
Yeah, that seems the most reasonable.
Who knows? I mean, I think other people have basically tried to. You can think about it like a tilt in the spectrum on small scales, which you could get by putting some neutrinos in. Not a large scale tilt, like an inflationary tilt, but a change in the shape on the smaller scales, which you might get by putting in something else. Or you might just not worry about it. We have to ask the people who know what the Planck data show. Okay, this leftover thing that comes from outside, this V external is 160 kilometers per second. Should you worry about that? Well, maybe, maybe not. Lambda CDM predicts that if you had a perfect sample sphere that went out to 200 H inverse megaparsecs, you'd only expect 40 kilometers per second in each component. So at face value, that's large. Of course, we don't know necessarily that it's coming from beyond 200 because there's missing data in the zone of avoidance. Okay, near in the galactic plane, there's also that part of the sky which doesn't go to 200. And finally, it's possible that our assumptions of linear biasing aren't perfect either. Right? We have a noisy density field, and we've assumed linear biasing to make those predictions. So in some sense, the difference could come from within this volume as well. So I don't worry about that too much at the moment. Another way of looking at it is from our data, we can predict what the bulk flow is within now a top hat, not a Gaussian. Okay, and so the model predicts when we add on this external flow plus the stuff we measure internally, predicts 700, and then that drops because of this extra 150 at the end. But it's not out of line from what you expect from a lambda CDM model. Okay, how much time have I got? About 5 minutes? All right, I will quickly take you through this. I'll just advertise this briefly. So the new way of doing this, I think, which is interesting, is the KSZ, kinetic Sunyaev-Zeldovich, which you know is a scattering of CMB photons off of objects now which are moving with respect to the CMB frame, traditionally done with clusters. Okay, but I'm going to show you a different way of doing it. I mentioned this Koszlinski measurement before, which was based on this, applying this in clusters, although other people had claimed that they'd underestimated their uncertainties. So this is a method of doing this from galaxies that we've applied to WMAP. led by Lavaux, who, as I said, was a CITA National Fellow, with Nayesh Shorty and myself. Remember that the KSZ effect measures the momentum of the electrons, okay? And to first order, everything's participating in the large-scale flow, so the velocities of everything is about the same, but most of the electrons are not in clusters, they're in the intergalactic medium. Okay, so what we did was to make a model using our velocity field, well, in this case using just a pure bulk flow, okay, and make a model of where we thought those electrons would be, assuming that they have some clustering like dark matter halos with respect to the galaxies themselves. Okay, so we use the nearby galaxies distribution as a template. Okay, that gives us the electron density field. We multiply that by some velocity field, which our models also predict, and that gives us a template that we can compare. I'm going to skip this for lack of time, but you can ask me about it later. Okay, so we fit that template to WMAP. Now the CMB is noise. Okay, and out of this exercise, we got a velocity 500 kilometers per second, plus or minus 250, 260. So it's not really a detection exactly. It's kind of just a borderline hint that something's going on, but still exciting. The direction, perhaps by chance, came out inconsistently with everything else that we'd measured before. Okay, the actual scale that we were measuring in WMAP was actually smaller, more local than this other stuff that I showed you, because the WMAP, with it, given its beam, was most sensitive to fairly nearby galaxies. Okay, so this was exciting. We did another measurement. So this is, let me go back a second. This one is based on only the objects that I just showed you in 2m++ that go to 200 megaparsecs, but most of the signal is really coming from within 50 megaparsecs. Okay. We also used all the galaxies that were in 2-mass period, whether or not they had redshifts, as a template, and just superimposed a bulk flow on them. And from that, we got an upper limit. So that's a much deeper sample. We got an upper limit of 500 kilometers per second on now a much larger scale, 500 H inverse megaparsecs. And that upper limit conflicts with the Kashlinsky et al. Claim on those scales. Now we're trying to improve this. We're trying to use the full velocity field that I've shown. Well, I haven't shown you pictures of the velocity from that density field to make a better template and to compare, of course, with Planck. Okay, so here are Lavaux's maps of what that template might look like from our data set. So these fluctuations in temperature are very small. Okay, but the important thing is they have a specific signature, which is, of course, localized where the galaxies are. And usually it's dominated by large-scale flows. This is mostly blue, and that's mostly red. But there's internal flows as well that we should be able to predict. So right now we're in the process of comparing that with Planck. Our predictions should be that we should reduce the errors by at least a factor of 3 when this is finished. And that'll be competitive with the other methods that I showed you before. Unfortunately, I was hoping to show you some results, but that analysis is still in progress at the moment, and we don't want to talk about it just yet. But I'll just say it looks promising. The errors are much lower than they were from WMAP, not surprisingly. The foregrounds, because of all the frequencies, have to be modeled better than they did before. The advantage when your errors are large, you can get away with a crude model. As your errors get down, you have to also pay more attention to the systematics. And the numerical inversions are more complicated as well, because the Planck data set's much bigger. So that's underway right now. And it'll be an interesting complement to other methods that people will use in Planck to measure KSC, like the infall of clusters, for example, and other similar techniques that have been done before. This is a different one that really depends on having a local map. All right, I may have used up more than my 5 minutes. I'll just say a few words about the future. Obviously, we can do better on the modeling side. For example, we can do better from the mapping galaxies into dark matter. Some of these methods for better nonlinear treatment, so going beyond linear perturbation theory, are in principle in hand. But probably most of the improvement is going to actually come from better data. And in particular, especially in Australia, the data sets are going to grow by factors of 10. They have big surveys underway. One of them is called Taipan, which will be bigger than that. I showed you the results from the 60F survey. This will be at least 5, maybe 6 or 7 times larger in terms of number of objects. So you can expect those error bars to come down further from that. There's another survey using the SKA Pathfinder called Wallaby, and there's a northern extension in the Netherlands called WINCHES, which will do H1 measurements. So they'll first map out redshifts, and then they'll also, for some of those, get Tully-Fisher. So the local measurements will get better from the redshift perspective, the mapping perspective, and also from the peculiar velocity perspective. And as I said, these will in total, the numbers will increase by a factor of about 10. So those errors that I showed you, in principle, if they were just random errors, they would shrink further by a factor of root n, but I'm sure we're going to hit some more systematics that we'll have to understand. But in future is actually quite good, especially when you fold in a third method, which is potentially kinetic Sunyaev-Zeldovich, to get another independent test of the same method. Okay, so that's the summary. I'll leave it up there since I'm over time. And I think that now we're entering this era, and it's coming especially from the Australian side, that we're getting more systematic large data sets with a more homogeneous data. SDSS surveys like Taipan and Wallaby that promise a new era for this type of work. Thanks.
Thanks, Mike. Any questions? Now, your KSC error bar, is that just from fitting it against WMAP?
Yes, so this one,
There's no like systematic template.
no systematic template error has been included in this number that I quoted.